Okay, so a big thank you to the organizers for inviting me to speak about my favorite topic, stellar magnetic activity. And as you already heard in the previous talk, there are of course also magnetic fields in hot stars, but what we're going to talk about here is we're going to talk about the cool stars, and that is stars that have an outer convective envelope or that are fully convective. And in terms of spectral type, we are talking here about mid-F or later. So for these cool stars, we have a magnetic dynamo operating in them, and this is fueled by the stellar differential rotation that is present on the surface of the star as well as in the interior of the star. And this causes the emergence of magnetic loops on the stellar surface. And when we look at some beautiful pictures of the sun here from the Solar Dynamic Observatory with the reconstruction of the magnetic fields, we see that these magnetic fields of cool stars are highly structured and localized, and they are variable over time. And the observable effects caused by this structured and time variable magnetic field is what we collectively call magnetic activity. There are quite a number of ways to observe manifestations of magnetic activity in cool stars. When we look at the stellar photosphere, for example in white light, we see star spots, and these are the areas where the magnetic field lines pierce the stellar surface and inhibit the convection. If we now move farther outward through the stellar atmosphere and go into the chromosphere here shown in the calcium-2 H and K lines, we find that those same regions where the star spots are bright in the chromosphere because the plasma is heated locally. And as I said, we can observe this in calcium-2, for example, and other lines that are important here are, for example, H-alpha or the sodium D lines. And if we move further outward, we finally reach the stellar or solar corona, where we see these beautiful magnetic loops filled with hot plasma of several million degrees, and this plasma emits thermally in soft X-rays. Such effects are time variable. We have short time variability, for example, in flares, but as we know very well from our own sun, we also can have long-term modulations of the stellar magnetic activity, for example, in the 11-year activity cycle. Now, the important point here is that cool stars not only operate a magnetic dynamo, they also shed an ionized stellar wind. And that means, because the wind couples to the magnetic field, that we have a loss of angular momentum over time. And so we start out with a young and active star that is quickly rotating and strongly magnetically active, and it quiets down over time to a slowly rotating star that is mostly inactive. We can observe this in any of your favorite activity indicators. For a young star, we have these very strong emission cores on the calcium-2 lines that are fully absent for older stars, and the same for soft X-rays, where we have very strong emission for the young and active stars. Now, if we look at the exoplanet zoo, I have plotted here the ones where we have mass estimates. Several people at this meeting have already pointed out that our current missions and planet detection techniques are very good at finding planets in this region here where we have the short orbits, and with new and upcoming missions we are about to fill in this space here more and more. But this part of the diagram here is very interesting because here we have systems where the exoplanets are in very close proximity to their host star, and interesting effects can arise there. If we look at one of those systems plotted to scale, we have here the WASP-12 system, we have a G-type host star, and we have a hot Jupiter in a one-day orbit, and this is actually drawn to scale. So what we see here is that the hot Jupiter orbits the host star within just a few stellar radii, and with the typical large coronal loop lengths, they can be something like this here. So we're actually in the vicinity of outer coronal loops with these orbits. This, of course, also means that these exoplanets are very strongly irradiated by the host star. And in such a case, we have an irradiation level that is about 100,000 times stronger than the irradiation of our own Earth. Now, this close proximity between exoplanet and host star brings up the question if there are interactions of exoplanets and their host stars. And there are basically two ways we can look at this. We can look at the question of planets influencing the stellar magnetic activity of their host stars. This is what we classically call magnetic star-planet interaction. And I will talk about this quite a bit and see what the observational evidence for this direction of the interaction is. And there's, of course, also the influence that stellar magnetic activity has on exoplanets. And this can have quite strong effects on the evaporation of exoplanetary atmospheres and also habitability. I will talk about this part a little bit at the end of my talk, but we will first focus on the other direction. So, star-planet interaction has been theoretically investigated for quite a while, starting with, for example, the initial papers by Coons in 2000, and there are two pathways for this interaction. There's the magnetic interaction, where the magnetospheres of the star and the exoplanet directly interact, and there can be reconnection events that we might be able to observe. And on the other hand, there's a tidal influence of the exoplanet onto the whole star, and it raises tidal bulges on the star that might interfere in some way with the stellar convection, and there might also be some kind of angular momentum transfer from the planetary orbit to the star. The initial, so to say, seminal discovery papers for this topic were done by Evgenia Shkolnik, and she observed a couple of hot Jupiter systems, and what we see here is one measure for magnetic activity. In this example, it's the calcium-2 line emission, and it is plotted here over the orbital phase of the exoplanet, not the stellar rotation period. And interestingly, there is indeed, for two of those systems, a modulation that seems to be in phase with the planetary orbit and not the stellar rotation, which was very interesting and very surprising, actually, to see it this strongly. However, recurring observations of these systems showed that the picture is quite a bit more complicated. Such modulations switched to the stellar rotation period, and a recent large observing program that has been reported by Scandariato et al., where one of these two systems, HD 179949, has been observed for a long time in Xray, so looking at the coronal magnetic activity. There's indeed some periodic change with quite some scatter, but the period that has been found is neither the stellar rotation period nor the planetary orbital period, so it's not quite clear what is actually going on here. Other things that have been observed and that are quite interesting but also quite puzzling for individual systems. We have here an X-ray light curve of the HD 189733 system, again hot Jupiter system. And Ignacio Piliteri and co-workers have observed several X-ray light curves with flares of the star occurring at a certain phase of the planetary orbit. And this is also quite surprising because we expect this to be stochastic basically for stars. But they have, with a new paper that came out, a third flare, again recorded at around about this orbital phase of the planet. And a possible interpretation is that there is a flaring loop connecting star and planet that just rotates into view. This here is the planetary eclipse that is indicated by those lines. But to make things more confusing, there are also examples of hot Jupiter host stars, in this case WASP-18, where the host star is a fairly young F6 star, but it is completely dark in X-ray. So we have here the optical image, we have here X-ray observations, this is just the exposure map, done by Brandon Miller and recently also by Piliteri and co-workers, and this star is completely X-ray dark. So why is this so weirdly inactive? This is a very confusing picture, and it's not quite clear in which direction we should expect effects to occur and how to observe them. There are some good news on the side of tidal interactions. There has been, for example, just highlighting one piece of work here. This is by Simon Albrecht, Josh Wynn, and co-workers, where they have looked at do the orbits actually come out in the pictures? It's okay. Where they look at the orbital obliquities, that is the misalignment of the planetary orbit with the stellar spin. And what they find when they look at stars of different spectral type, they find that for cool stars with convective envelopes, that is stars where we expect a stronger tidal interaction between exoplanet and host star, these obliquities or misalignments tend to be small. Whereas for hotter stars, where the tidal interaction is expected to be weaker, the spread of orbital obliquities is quite large. So this might actually point to some tidal interaction effects that bring the spin and the orbital plane in line. So if the picture is a bit confusing on the individual system side, maybe we can work with samples of exoplanet hosting stars and look at magnetic activity effects and see if we can detect those maybe weak effects in large samples. So what we would expect here is that for systems like this, where we have massive planets in close-in orbits, we expect preferentially high activity of the host star, whereas for a system like this, where we have a small planet or a far-out planet, we expect for them to be preferentially of lower activity than the other sample. The number of people have searched for these effects, Vinay Katja, Evgenia Shkolnik, myself, and we have to be a bit careful in interpreting what we find. So let me show you a typical example. This is what we typically find. So what we have here on the x-axis is the planetary mass divided by the semi-major axis, and we have here a measure of stellar, activity. In this case, far UV emission. And what we find here are generally weak trends where we have a somewhat upward trend toward the stars that host hot Jupiters, with some more scatter on this side here. And this is a consistent picture that we find with many activity indicators, a very weak trend with large scatter. So the question is, do we want to interpret this trend, or do we want to be very careful with this? And I think we should be very careful with this, and the reason is this. We are not dealing with a fully unbiased sample here. We actually have quite some selection effects in our detected exoplanet host stars. If we, for example, have a star that is slowly rotating and fairly inactive, and compare that to a star that is fast rotating and quite active, and we put some hypothetical planets around them at different masses and different distances, with a quite good data set for this inactive star, we will detect those planets after a while if we get good enough data. But with the same data quality for a very noisy, active star with lots of variability, we might get unlucky and just detect those planets that produce the biggest detection signal, and this is generally hot Jupiters. So what we have here is just a selection effect for only finding the hot Jupiters around the very active stars, unless we have a superb data set to also find the other planets. So if we look at it this way here, again, we have a measure for the planetary mass and the looking at the distances, and here we have the Xray luminosities. This typical picture that we have a larger spread here for the hot Jupiters and a smaller spread here for the smaller exoplanets is very likely a selection effect, and especially it is strong for radial velocity searches. It gets a little bit better including transiting systems. For example, we have here the Kuro 7b exoplanet that orbits a quite active host star, and as many of you might remember, it was actually quite a pain to figure out what the mass of this exoplanet was, even though it was already detected via transits. But since the host star was so active, it was really hard to find the RV signal, even when we knew where and when to search. So what can we do about this? We have this activity decline with stellar age. And the problem is when we look at these planet hosting samples that we have a variety of ages. We're typically here in this regime, so we have saturation for the very young ones, and Anne-Marie Cody is talking about this stellar age regime here. But for our exoplanet samples, we're usually here in this range for the old stars. And typically, if we find a young one, it is here, and we see the hot Jupiters, and we go to the very old ones for our super Earths. So what we actually need to really test for the occurrence of star-planet interactions in this way is we need to pin down stellar ages and find true activity outliers and see if they're actually there. And astroseismic ages can help us here a lot. We can test for these outliers with a variety of observables, for example, with stellar rotation here, and there we're pointing to the tidal interaction regime. We can look at the activity in the chromosphere and look for outliers compared to stellar age. We can look at the activity in the corona, where we see the soft X-ray emission. And finally, this is some recent work from Alini Vidotto and co-workers. We can also look at the global part of the stellar magnetic field that is detectable, and that also changes over time. So we have a variety of observables that we can look at once we know stellar ages and look for these outliers. What we also can do to get a little bit of a handle on these stellar ages is that we can look at systems where we have wide stellar binaries in which one of the stars hosts a planet and the other one doesn't host a planet, or is at least not known to host a planet. And we can actually compare the activity levels of these two stars, because if they form a physical pair, they should have around about the same age. So after adjusting for spectrotype differences, they should display the same activity level if there's no planetary influence at all. So we have recently performed X-ray observations of these 5 systems, and we have 15 more systems coming up, and I'm just showing you a few examples here. For one of those systems, the Uppsala Andromeda system, where we have a quite hot host star and expect weak tidal interaction between exoplanet and host star, we find this. We find the secondary without a known planet to be at this X-ray luminosity level, which is consistent with a fairly old age of the host star. And primary, which hosts a planet, is also at a fairly low X-ray activity level. It is of an earlier spectrotype, so it's a bit brighter, but it is consistent with old age, as we would expect. Now, if we look at 2 other systems where the planet hosting stars are of later spectrotype and we expect stronger tidal interaction, the picture changes quite a bit. There we have the secondaries in those systems. This is CoRoT2b and HD189733b. And again, the secondaries are fairly X-ray dim, consistent with old age. Now, what we would expect for the primaries is to have the X-ray luminosity level somewhere here for K and G dwarfs, somewhere in this region. But what we actually find after observing them is that the planet-hosting stars are X-ray brighter by 1 to 2 orders of magnitude, which is quite surprising and quite larger than the scatter we would expect from these relationships. So we are possibly seeing some manifestation of star-planet interaction here in these stars being overactive compared to an actual age comparison that we can do with the secondaries in these systems. So if we show our 5 systems here, we have here the X-ray luminosities of the secondaries in red, and the expected range for coeval primaries that host the planets in these blue boxes. And for the cases where we expect weak tidal interaction, these agree well. And for the other 2 cases, they are fairly far apart from what you would actually expect. So this might be a way forward to disentangle the age effect and an actual effect that exoplanets might have on their host stars. Now I would like to talk for a little bit about the other direction of the interaction between stars and exoplanets, because stellar activity does affect the exoplanets, of course. We have such effects like stellar flares, we have coronal mass ejections, and of course we have the stellar high energy emission that impinges onto the exoplanetary atmosphere, and there we have heating of the high altitude layers, and we can have quite substantial planetary mass loss that has been observed in a couple of cases. This evaporation is mainly driven by X-rays and UVs because they are absorbed high up in the atmosphere, and there are quite a number of theoretical models by, for example, Ruth Murray Clay, but also by other authors that earlier worked on the effect that this high energy irradiation has on the atmospheres. The general agreement these days is that for hot Jupiters, we can actually observe this evaporation, but if we calculate the mass loss over the lifetime of the system, as a fraction of the total mass of the exoplanet, it is really small for hot Jupiters, but it can become really substantial for super-Earths and mini-Neptunes. And what I'm showing here is the work by Eric Lopez and co-workers, where they looked at several super-Earths and start out in their model with a substantial hydrogen-helium envelope and look at the stellar evolution of X-ray and UV luminosity over time and integrate this model and look at the mass loss of the exoplanets. And depending on what the orbital distance is that you have to your host star, you can basically evaporate such a mini Neptune down to a rocky core, whereas when you are in a larger separation from the host star, you lose quite some of the envelope, but not all of it. And this might explain several systems that have been observed by Kepler, where we have mass estimates and where we have a high density planet in a very tight orbit around the host star and a lower density exoplanet at a somewhat larger orbital separation. Something that we can also observe and that is closely related to that is the extent of the outer exoplanetary atmospheres themselves, and we can study them with the same observations basically that we use to determine the mass loss. The point here is that X-rays and UV photons are absorbed high up in the atmosphere, and we know this from our own Earth. So the radius of our own Earth is about 100 kilometers larger in X-rays than it is in the optical. And we can use this for inflated hot Jupiters, for example, to probe the densities and the extent of their atmospheres. And quite a number of observations have been done in the UV and also in X-rays where deeper or also asymmetric transit profiles have been found at short wavelengths and that point to quite complex extended atmospheres that we have there. But all of these observations, as you can see from the scatter and the error bars, will greatly benefit from upcoming opportunities with larger effective areas in this wavelength regime. Another interesting thing when we have very strong evaporation and mass loss is that we can even observe it at optical wavelengths. For example, we have here this Kepler source reported by Saul Rappaport and co-workers, where we have this very peculiar transit profile here in this asymmetric sort of tail that we see. And this has been interpreted as a sort of cometary evaporation tail where we have dusty particles being evaporated from that exoplanet. And there's a very interesting poster about multicolor observations of this transit and systems like this, and to see basically what the dust grain sizes are. There's some very interesting work to be done. What would be really great for such a system to observe is, of course, what is the X-ray and UV emission of the host, and what is the actual energy budget that might be driving such processes. Unfortunately, for many Kepler targets, they are so far away that we don't really reach that far with our X-ray and UV telescopes. But what has been done, and what closely relates to this, is one can look at the star spot variability of that system. So what we see here, thank you, what we see here is the transit depth of the exoplanets. So we have deeper transits here, shallower transits here. And what we see here is the phase-folded light curve of the star, folded with the stellar rotation period. And what we can see that at phases where the star is dimmer, because lots of star spots are pointing our way, the transits of the exoplanet get deeper, because the evaporation is fueled by that activity of this stellar hemisphere that is rotating into our field of view. So there's some very exciting stuff here to be done, and once we find closer systems or have better telescopes that are coming up in a few years, we can directly observe the energy budget for this. I would like to show you one more example where we have some exciting news here. We have recently been able to detect the host star of the super-Earth GJ1214b in soft X-rays. This is work that has been led by Lalita Sairam. And we have here a clear detection of the host star in X-rays. And we actually have a light curve where we have a stellar flare detected, and we can look at different energy bands. And the really interesting point here is that for this system, the X-ray and extreme UV flux at the planetary orbit is fairly large, and it is at least 5 times higher than for the hot Jupiter HD 209458b. And this is very important because this hot Jupiter has been observed to be actively evaporating. So we can expect that this super-Earth is evaporating as well, and this might present some very interesting observational things that we can do because the system is very close to our own sun and easily observable. So if you want to know a bit more about this or exchange ideas, please find in the coffee break. To look at such planetary evaporation scenarios, it is of course important to know the exoplanetary densities and masses. And I would just like to quickly alert you to a project you may have heard a little bit about already. This is the KOInet to constrain masses of exoplanetary candidates from Kepler. This is led by Carolina von Essen at Aarhus University, and this is an optical ground-based observing network to follow up on transit timing variations observed with the Kepler Space Telescope. And if you would like to get in touch, please contact her. She is fantastic, or visit the project website. Now I would like to summarize what we have learned over the last couple of years about stellar magnetic activity and exoplanets. We do know that we have strong stellar activity biases in the samples of known exoplanet host stars, and we need to work around that to be able to figure out if there's actually consistently some star-planet interaction going on for hot Jupiter systems or not. There are some interesting but sometimes confusing observations of individual systems where we may have flare triggering, where we may have tidal interaction that we are seeing here, but we clearly need a much larger observational database for this stuff. We do need activity-independent age estimates, and that's why astroseismology is so exciting to us, to identify true outliers from an age-activity relationship. And finally, on the exoplanetary side, we do want to understand stellar magnetic activity and its evolution because the X-rays and UV drive the evaporation of exoplanets. And with this, I'd like to thank you for your attention and take questions.
Thank you very much. Any questions for Katja? I see one from Jamie down here. Well, while the microphone is making its way, I had just a small comment really on the evaporating KOI from Kepler, the low mass one. The fact that you see deeper transits when the star is fainter can also be due simply to this, the transit chord being over a part of the star that's not so spotty.
That is true, that is true. If you don't know where, for example, the spot belts are on the star, that is definitely an alternate explanation, yes.
Just in terms of the history of star-exoplanet magnetic interactions, you neglected to mention most had detected in the Tau Bodas system synchronization of the light variability with the planetary orbital period, which a non-transiting system, and we looked at every possibility to explain it, tidal, interaction, backheating, and the only explanation that was plausible was an interaction of the planet magnetosphere with the star's magnetic field, and that was confirmed by CFHT Espedon's spectropolarimetry, the first paper led by Claude Català, but Evgenia Shkolnik was a co-author on that, showing that the magnetic field was in fact concentrated very close to the subplanetary point.
Yes, you're definitely right. The Tau Bodas system is a very exciting example of that.
Any other questions for Katja? Sorry, I can't see very well. So. Yes, Xray and...
Yeah, I have to say I really appreciate how you're inverting the paradigm. If something confuses the bejesus out of me, and I just want to walk away if it's got a magnetic field, and you're kind of inverting that, and you're embracing the messiness of these magnetic fields, and I think that's great. You showed a plot of the X-ray luminosity versus age, and you showed a very narrow line for your theoretical prediction of what that X-ray luminosity should be. How big are your uncertainties in that, and can you actually use that to better constrain these things?
So actually these lines are just to guide the eye, because these are not the actual predictions. So what I'm trying to show here a little bit with these bluish boxes is sort of the typical scatter that we would expect when we think of what do we see for the secondary and what range might we expect when we know the spectrotype of the primary and correct for that. So this is not as precise. There is some fuzziness here. And especially if you're only talking about a factor of 5 or so, this is definitely within the range of scatter that we might just be seeing there. Also just from stellar activity cycles, there are some interesting observations of that now. But an order of magnitude or even 2 orders of magnitude is quite hard to explain as a random effect.
There was one question from Simaze.
Yeah, the claim that you see activity with the orbital period of the planet is, I think, not very well established. You know, all the announcements that were in the past, and I at that time already I wasn't convinced, because there are not many events and they can look as if they are associated with the orbital period, and before I see some kind of periodogram with a significant peak, I think we should be careful. And what happened is that with some of these announcements, as you said very nicely afterwards, the picture is more complicated, or something like this, which is something that, you know, that the skeptical reader before could predict.
Yes, so there are definitely big challenges there. And I think one of the problems is finding a good test system for this, because in every star you expect some stochastic activity stuff that can, if you're observing cadence, just lines up right or unfortunate actually, that it mimics something like that. So I think what we actually need to do for some of these cases, we need a very good system where the whole star is intrinsically very inactive. So if we see something, I mean these features should be weak. We need a very inactive star with a very nearby hot Jupiter where we can be fairly certain that we're actually seeing something that is exoplanet-induced and cannot be confused with a random stochastic flaring event. Yes. Yes, definitely.
Okay, we have time for one last question.
Just by looking at all the magnitude of these flares, and magnetic luminosity, and also other stellar flares, I think one can this is just common. I think it's just looking at all the magnitude of this. I think one can reasonably confidently draw the conclusion that this kind of energy, luminosity, cannot be directly supplied from planet orbital motion because from theoretical point of view, one can derive a reasonably clean upper limit of how much energy you can supply from the orbital motion, the rate at which you can supply.
Right,
to the
otherwise
thing.
you spiralate.
And basically, that upper limit, I think the really clean upper limit, is several order of magnitude smaller than this, I think, if I remember.
Oh,
And
well,
of course, having said that, it's also true that the planet can indirectly affect the magnetic flares, so that energy
Right.
with energy coming from the star. So
Right. Exactly. So this is one of those points that have been made more in recent years, because exactly that energy budget constraint came up, that basically the idea is now that if a planet's magnetosphere pass along a coronal loop that is already tangled up, that it might be just that little push that triggers it to flare. But of course, this needs very good data to be really confirmed. Yeah.
Okay, let's thank Katja again.
Thank you.